Where atoms come from. We are all star stuff. We've learned about how some of the elements were discovered and how they were organized, but where do elements come from? To answer that question, scientists had to figure out where we come from. The answers, of course, could be found in the periodic table. The Big Bang and other theories. The view that dominated science for centuries was that elements don't come from anywhere. So then, where did people think they came from? Well, the thought was that the lifetime of every element was the same as the lifetime of the universe. They're neither created nor destroyed. Elements just are. Later theories, such as the 1930s Big Bang Theory, said that whatever existed back then, 14 billion years ago, contained all the matter in the universe. Everything around us must have started at that point. Not shaped like diamond tiaras and tin cans and aluminum foil yet, but of the same basic stuff. One scientist calculated that it took the Big Bang 10 minutes to create all known matter, and then joked, "The elements were cooked in less time than it takes to cook a dish of duck and roast potatoes." Over the next few decades, that theory began to be questioned. By 1939, German and American scientists had proved that the sun and other stars heated themselves by squashing two hydrogen atoms together to form helium, a process that releases a large amount of energy. Some scientists said, okay, the amount of hydrogen and helium may change because of this reaction, but only slightly, and there was no evidence of the amounts of other elements changing at all. But as telescopes kept improving, data showed that most young stars contain only hydrogen and helium, while older stars contained dozens of elements. Plus, extremely unstable elements such as technetium, element 43, which doesn't exist on Earth, does exist in certain stars. The stars must therefore be making new elements every day. In a mid-1950s scholarly paper, astronomers Geoffrey Burbridge, Margaret Burbridge, William Fowler, and Fred Hoyle explained a theory they called stellar nucleosynthesis. The paper, known simply as B squared FH, which represents the last initial of each contributor, first suggests the universe was a big mess of hydrogen with a little helium and lithium, element 3. Eventually, hydrogen atoms clumped together into stars to produce helium. Only when the hydrogen burns up, B squared FH suggests, do things start happening. It can be best described as evolution for elements. The paper explains how hydrogen, through various reactions, produces every element up to iron, element 26. As a result of B squared FH, once you've found iron in a star, you don't need to bother looking for anything smaller. Once iron is spotted, it's safe to assume the rest of the periodic table up to that point is there too. You may think that iron atoms soon stick together in the biggest stars, and that the resulting atoms fuse together, forming every element on the rest of the periodic table. Not so fast. When you do the math and examine how much energy is produced, you will find that fusing anything to iron's 26 protons costs energy. That means mashing iron atoms together does an energy-hungry star no good. Iron is the final element in a star's natural life. So where do the heaviest elements, 27 through 92, cobalt through uranium, come from? Ironically, says B squared FH, they emerge ready-made from mini Big Bangs called supernovae. After burning through smaller elements, extremely massive stars, 12 times the size of the Sun, burn down to just iron cores in about 1 Earth day. But before dying, these burned-out stars implode under their own immense gravity, collapsing thousands of miles in just seconds. In their cores, they even crush protons and electrons together into neutrons. Then, rebounding from this collapse, they explode outward, creating a supernova. For one glorious month, a supernova stretches millions of miles and shines brighter than 1 billion stars. And during a supernova, so many gazillions of particles with so much momentum collide so many times per second that they high jump over the normal energy barriers and fuse onto iron. many iron atoms gain neutrons, some of which are converted into protons. Because the number of protons determines an atom's identity, new elements are created. Every natural combination of element spews forth from this particle blizzard. One such supernova explosion created our solar system. About 4.6 billion years ago, a supernova sent a sonic boom through a flat cloud of space dust about 15 billion miles wide, the remains of at least two previous stars. The dust particles mixed with the supernova and created a huge cloud. The dense center of the cloud boiled up into the sun, and planets were formed from the leftovers. But not only planets. The leftovers also include everything around you right now: books, walls, table, food, everything. Even your own body was once part of a star. As the late astrophysicist Carl Sagan said, we are all star stuff. Two types of planets. The planets provided the names of many elements as well. Uranus was discovered in 1781, and despite the fact that it contains basically 0 grams of the element, a scientist named uranium after it in 1789. Neptunium, element 93, and plutonium, element 94, followed from Neptune and Pluto. Pluto used to be referenced to as one of 9 planets in our solar system, but as of 2006, it's no longer classified as a planet. It's now a dwarf planet. But of all the planets, Jupiter, a gas planet, has had the most spectacular run in recent decades. In 1994, comet Shoemaker-Levy 9 collided with it, the first intergalactic collision humans ever witnessed. It didn't disappoint. 21 comet fragments struck the planet, and fireballs jumped 2,000 miles high. The history of our solar system's rocky planets, Mercury, Venus, Earth, and Mars, is different from that of the gas planets. When the solar system formed, the gas planets, like Jupiter, formed first, in as little as 1 million years. The heavy elements gathered nearby, well, relatively, and stayed quiet for millions of years more. When the Earth and its neighbors were finally spun into molten globes, those elements were blended more or less evenly inside them. In theory, you could have scooped up a handful of soil and held the whole universe, the whole periodic table, in your palm. But as the elements churned around, atoms began joining up with their twins and chemical cousins until eventually large deposits of each element formed. Dense iron sank to the core inside each planet where it rests today. When the Earth cooled and solidified, we were left with clusters of elements all over the planet. Elements and the age of Earth. Given that our solar system's formation took place incomprehensibly long ago, reasonable people may ask how scientists have the foggiest idea of how the Earth was formed. Basically, scientists analyzed the amount and placement of common and rare elements in the Earth's crust and deduced how they could have gotten where they are. For instance, the common elements lead and uranium fixed the birth date of our planet through a series of insanely meticulous experiments done by a graduate student named Claire Patterson in Chicago in the 1950s. Patterson used pieces of a meteor to figure it out, since meteors formed from the same dust the planets did and have floated around in space unchanged since then. They are basically just hunks of the original Earth. His findings? That our planet is roughly 4.55 billion years old. His experiments, which involved lead, also resulted in another important discovery: that lead levels in our atmosphere had been rising because of all the materials people were using in it, such as pipes, paints, and gasoline, and that this was bad for people and for our environment. Patterson became an important environmental campaigner. And he's the main reason future children will never eat lead paint chips and gas stations no longer to bother to advertise unleaded on their pumps. Thanks to Patterson, it's common sense today that lead paint should be banned and cars shouldn't vaporize lead for us to breathe in. Trying to find out how old our planet is helped keep it and us healthy.